In our video today, we're going to learn how to add and subtract on a number line. And in our first example, we're told that we received $10 from our grandmother for her birthday. You spent $4 on snacks. Using addition, all right, how would you write a number sentence to represent this example? So we're going to start off by writing a number sentence that uses addition. Okay, so if grandma gave us $10 for our birthday, the amount of money that we have has gone up by 10, so that's going to be a positive 10 to represent that. And then I'm using addition, so I'm going to add some number. It says that I spent $4 on snacks. So when I spend money, the amount of money that I have is going to go down. So to represent spending $4, I'm going to add negative 4. This number sentence represents our example, 10 plus negative 4. What we're going to do is model this on a number line to figure out the answer. Now, we've been working with operations or specifically adding with rational numbers, and so I think we can figure out the answer without doing a number line, but I do want to model how we could do this using a number line. In order to use a number line to show the answer to this problem, we will draw vectors that represent the size and direction of the numbers that are being added. All right, so what we're going to do, we're going to take this problem, 10 plus negative 4, and we're going to model it on this number line down here. Okay, so letter A, it says place the tail of the first vector on blank. Well, we need a vector to represent each number in our addition problem. Our first number is the number 10. When we draw the first vector, we will always begin at 0 on our number line. So we're going to place the tail of the first vector on 0. Okay, so I'm just going to put a little dot right there. That's where the tail of my first vector is going to begin. And since the first number in the problem is 10, we're going to draw the first vector 10 units to the right of 0. And we're going to be stopping at the number 10. Okay, so let's go ahead and draw that. If we draw a vector, which again is an arrow, 10 units to the right of 0, it's going to look something like that. Okay, because this vector is 10 units long and it's moving to the right, I'm going to label this vector as a positive 10. All right, now the direction of that vector was to the right because the first number was a positive number. Had this been a negative 10, our first vector would have gone 10 units to the left. Okay, so there's our vector for the first number, positive 10. Now I need another vector that's going to show that we are spending $4 or adding negative 4. So letter C, start the next vector at the end of the first vector, which was here at 10. So right above this vector, I'm going to put a little dot right here, and that's where my next vector is going to begin. Draw the second vector 4 units to the left since you are adding a negative number. Okay, because we're adding negative 4, this next vector has to be 4 units long, but it has to go to the left, and it would look something like this. Okay, so it's 4 units long, it's moving to the left, so I'm going to label this vector as negative 4. 10 plus negative 4, at the end of this vector, we have our answer, which we see here, is positive 6. So going back up here, 10 plus negative 4 equals 6. All right, so this is how we can use a number line and vectors to show our answer to addition problems. In our next problem, we're going to model the sum of negative 2 plus 3 by drawing vectors on this number line. All right, so I'm going to have two different vectors, one for each part of the addition problem. My first number is negative 2. Our first vector is always going to begin at 0. So I'll put the tail of my arrow there on 0 rather. And since my first number is a negative 2, I have to draw this vector 2 units to the left of 0, stopping at negative 2. And I can label that vector now as negative 2. My next vector is going to start where the first one ended. So right above negative 2, above that vector, I'm going to put a little dot right there to start my next vector. And now I'm going to be adding a positive 3, which is going to take me 3 units to the right of negative 2. So let's go ahead and draw that vector, 1, 2, 3 units to the right. And again, I can label that as a positive 3 because it's 3 units long and moving to the right. And now if I look at my number line here, I can see that if I add negative 2 and 3, negative 2 plus 3 equals a positive 1. Example 3a, repeat this process for the expression of 3 plus negative 2. So again, we're going to start our first vector always at 0. This time, our first number in the problem is positive 3. So I'm going to be moving 3 units to the right of 0. All right, and I can label that as a vector representing positive 3. My second vector begins where the first one ended, so at 3. And because I'm adding negative 2, I need to move to the left 2 units. 1, 2. And I can label that vector now as negative 2. And so if I wanted the answer to 3 plus negative 2, well, just follow the vectors. 3 plus negative 2 equals positive 1. All right, notice these two examples. We had negative 2 plus 3. We had 3 plus negative 2. What can you say about the sum of negative 2 and plus 3 and 3 plus negative 2? The sums are the same. In each example, we had an answer of 1. The answer was 1 in each case. Does order matter when adding numbers? Well, no, it doesn't. No. Order does not matter. Order does not matter because we know that addition is commutative. All right, the commutative property of addition says that you can add numbers in any order and you will get the same answer. So again, the order doesn't matter when adding numbers because addition is a commutative operation. In our next example, we're told that a football team gains 3 yards on first down and loses 8 yards on second down. Write a subtraction problem that represents this situation, and then we can model the subtraction again on our number line, drawing our vectors. Okay, so our football team, they're gaining 3 yards on first down. By gaining 3 yards, all right, that's going to be represented by a positive 3. But on second down, they lose 8 yards. So that means if I'm writing subtraction, I'm going to have to take away 8 yards. 3 minus 8 is the subtraction problem that represents this example. Let's figure out the answer to 3 minus 8, again, by drawing vectors on our number line. Just like we did with addition, when we're doing subtraction on the number line, our first vector has to start at 0. And our first vector has to represent the first number in the subtraction problem, which is positive 3. So I'm going to draw my first vector 3 units to the right, ending at 3. And there's my vector positive 3. Similarly, our second vector is going to start where the first vector ended. So here at 3, I'm going to put my little dot there where my next vector is going to begin. And since they lost 8 yards, since I'm taking away 8 of those yards, my next vector is going to have to go 8 units, but to the left. So let's move 8 units to the left. That's going to take us down here, ending at negative 5. So the length of this vector is 8 units, but since it was to the left, this vector represents the number negative 8. And so now, if we want the answer to 3 minus 8, well, follow the vectors. 3 minus 8 equals negative 5. Now, remember that you can always change subtraction into an addition problem. If I wanted to write this as an equivalent addition problem, I would keep 3 the same, keep the first number, but instead of subtracting 8, I would add the opposite, which is negative 8. 3 plus negative 8. And again, I can see that here in this problem. There's my positive 3. I'm adding negative 8, which again gets me to negative 5. All right, so keep that in mind when you have a question kind of like number 5 here. Model the subtraction problem 4 minus negative 6 on the number line by changing the subtraction into an addition problem first. All right, 4 minus negative 6. That can get a little tricky. But remember that subtracting negative 6 is the same as adding negative 6's opposite. So I can keep 4 the same, keep that first number, but instead of subtracting negative 6, I can just add positive 6. So subtracting negative 6 and adding positive 6 are the exact same thing. Let's model this on the number line. Our first vector starts at 0. The first number in our problem is positive 4, so let's go 4 units to the left of 0, and that vector is positive 4. And again, taking away 6 negatives is the same as adding 6 positives, so our next vector starts at 4, but it's going to move 6 units to the right, and we've ended here at positive 10. All right, so this vector is positive 6. 4 minus negative 6 is the same as 4 plus 6, which gives us a value of 10. So again, any of your subtractions change into an equivalent addition problem first, and then you can easily model on the number line by drawing your vectors. Our next example asks us to plot all of the numbers that are 5 units from 3 on the number line below. Okay, now remember, to plot a number on the number line, you're going to put a dot on the number line where that number is located. So we want to be 5 units away from negative 3. It doesn't specify which direction, so we can go either direction. So here's 3, 5 units away. Well, I can go 5 units to the left, 1, 2, 3, 4, 5, so I could be at negative 2. Or from 3, I could be 5 units to the right, 1, 2, 3, 4, 5. I could be here at positive 8. Okay, so these two dots represent the numbers that are 5 units away from from positive 3 on our number line. What we're going to do is write some number sentences that could be used to find each point. All right, so if we think about the number negative 2 to begin, all right, I wanted to be 5 units away from the number 3. I'm going to create a number sentence that's going to get me from 3 to negative 2, which means in my number sentence, the first number has to be a 3. Okay, so I'm going to start with 3. Now, if I'm at 3, to get to negative 2, all right, well, I'm going to have to figure out what I'm going to need to do mathematically to get there. So let's start by drawing a vector that represents the number 3, and then we can figure out how to get to the number 2. Our vector, of course, starts at 0. And to show the number 3, we're going to move 3 units to the right of 0. And there we are. Now that we're here at 3, in order to get to negative 2, I'm going to have to move in the direction to the left. And if I count that, again, that was 5 units to the left. Since I'm moving 5 units to the left, this vector here is going to represent the number negative 5. Okay, so one way that I could represent this problem is 3 minus 5. 3 minus 5 equals negative 2. But remember, subtraction can be changed into addition. Subtracting 5 is the same as adding negative 5, and we would get the same answer. So this picture right here could either be 3 minus 5 or it could be 3 plus negative 5 because they are equivalent. What about this point over here at 8? Well, again, my first number in my problem, since I'm 5 units away from 3, has to be a 3. So here's my vector again, starting at 0, going to 3. But now my second vector is going to start at 3, but move to the right 5 units. And since this vector is 5 units long moving to the right, that's the vector representing the number positive 5. So one real easy number sentence that we could create is 3 plus 5 equals 8. All right, now we could come up with another number sentence. All right, I probably wouldn't ever come up with this in most of the cases, but it is one that is equivalent. All right, subtracting 5 is the same as adding negative 5, which means that adding 5 must be the same as subtracting negative 5. All right, subtracting negative 5 is the same as adding positive 5. In each case, you would get the value of 8. Okay, so those are the different number sentences that we can use to find all the points that are 5 units away from 3 on the number line. In our next example, they want us to figure out what the temperature is going to be. They tell us that on a cold night, the temperature started at 5 degrees. Overnight, the temperature dropped 8 degrees, but by noon the next day, the temperature has risen or rises by 12 degrees. What is the temperature at noon? Show your work on the number line. All right, so they reference 3 different things in this example. We have our starting temperature, we have a decrease of 8 degrees, and we have an increase of 12 degrees. Since I have those 3 different items here, I'm going to draw 3 different vectors on this number line. Let's go with the starting temperature first. I have to start at 5 degrees. So to show that, I'm going to start at 0, as I always do with my first vector. And to get to 5 degrees, I'm going to draw my first vector 5 units to the right of 0. And there we have it. That vector represents the starting temperature of 5 degrees. Now we need to show what happens overnight. Well, overnight the temperature drops 8 degrees. So I'm going to start my second vector at the end of the first vector, so at the 5 degree mark. And if we're dropping 8 degrees, that means that we're going to be moving to the left 8 units on our number line. So let's go ahead and draw a vector moving to the left 8 units. All right, that got me 5 units to the left, back to 0, 6, 7, 8 units to the left, which means I've stopped here at -3 degrees. This vector is 8 units long to the left, so that is the vector for -8. Now, during the day, by noon the next day, the temperature rises 12 degrees. So we're going to start our third vector at the end of the second vector. And now we're going to show a 12-degree rise, which means we're going to be moving to the right 12 units. Okay, so I'm at -3. And if I move 3 units to the right, I'm back at 0. So I need to move 9 more to the right, which means this vector right here is going to end at 9. This vector is 12 units long moving to the right, so I'm going to label that as a +12. Okay, so here is our number line that allows us to figure out the temperature. 5 degrees was the temperature to start. It dropped 8 degrees overnight. By noon the next day, it rises 12 degrees. So at noon the next day, the temperature here, it is 9 degrees. We could show that mathematically a few different ways by using the vectors. Okay, our first number in our problem could be the number 5. And then my second number, or my second vector, represents the number -8. So I could add -8 degrees to that for the 8-degree drop. And then I could add 12 more in order to figure out what the temperature would be after the temperature rises. 5 plus -8 is -3, and -3 plus 12 is equal to 9. So that's one way that you could show this problem. You also could have said 5 minus 8 plus 12 equals 9. And again, that would accurately represent what we see here with the vectors in our picture.